All right, let's talk about water phase change and how energy is required and released as water changes phases. So, this is a potential energy diagram, and what we know about water is that it exists in three different phases. We have solids, liquid and gas, right? Which we're going to call vapor here before too long. So I've got some freezing and boiling temperatures of water here. And so zero is the temperature that we know water to begin to start phase changing from a liquid to a solid. We call that the freezing temperature. It's also where liquid water, well, the 100-degree mark is where liquid water begins to boil, and that's known as vaporization. Okay, so we've got this range of temperatures between 0 and 100, and I'm gonna draw this line that goes up like this. And this represents all of the temperatures between 0 and 100 that liquid water can be at. Okay, and what we know about liquid water is that it takes 4.2 joules of energy to get 1 gram of that water to change temperature by 1 degree. Okay, so the equation that we use here is delta H equals Cm delta T. Okay. So that's actually just a review of what we have already known. We know that water exists at 0 degrees as well. And I'm going to draw a straight across line right here. This is where we have a mixture of liquid and solid. Okay, this is a tough one for students because we basically feel like, you know, once water gets to 0 degrees, it should just go ahead and freeze into a solid, but it doesn't really happen like that. It freezes kind of gradually, and as long as there's a mixture of liquid and solid, according to the chemistry, it should be at 0 degrees Celsius. Okay. The same is true up here with our vaporization point, or our boiling temperature of water. This is a liquid and gas mix. Okay, and so as long as the liquid and the gas are mixed together, then that solution should be a 100-degree temperature. Okay, now we can get this line to continue going up above 100, but it won't begin to climb above 100 until all of the liquid is gone. And the same thing is true down here. The solid, the ice that you're thinking of, will go below 0 degrees, but not while there's liquid water mixed in. So once the entire liquid sample completely solidifies at 0 degrees, then you can start to bring the temperature down below that. So we are gonna think about like how much energy is required to move from, you know, a solid to a gas, or how much energy is released as a gas condenses into a liquid, that sort of stuff. Okay, so just as a review, 4.2 joules of energy are either absorbed or released as 1 gram of water cools off or warms up by 1 degree Celsius. So we're talking about just 1 gram of water in this long stretch of graph right here. Of course, we work with lots of different amounts of water, but the equation is good for just the one gram. This number is specific to 1 gram of water. Okay, so let's talk in particular about these flat portions of this line. Okay, and those have two kind of special names. Those are known as the molar heat of fusion and the molar heat of vaporization. And they're sort of similar to the specific heat values. They're amounts of energy required to sort of do something to water, but they're different in that they work with a mole of water instead of a gram of water. And a mole of water is like 18 grams, right? Remember the H2O. We have the molar mass of oxygen is 16, molar mass of hydrogen is 1, and we got 2 of them, so that makes 18. Anyway, so it's the amount of energy required to make 1 mole of solid water into liquid water. So it's basically how much energy it requires to melt 1 mole of water. Or it could go the other way. It could be the amount of energy that is involved with 1 mole of liquid water turning into solid water. So it's either the amount of energy lost by liquid water to become solid water, or it's the amount of energy gained by solid water to become liquid water. Okay? And then molar heat of vaporization is the same idea, but instead of the phase change between up here, remember this is the phase change that was between liquid and solid, so back and forth between liquid and solid. Heat of vaporization, this is where we're moving between liquid and gas, and I'm going to use V for vapor just to be technically correct here. So here we're talking about the amount of energy it takes to transform some liquid water into vapor water or gaseous water, okay? And we just call that the heat of vaporization. And it's the amount of energy required to make 1 mole of liquid water into steam, which is vapor, or it's the amount of energy lost by 1 mole of steam to become liquid. So when you think about that gaining and losing energy, remember that this is a potential energy graph, and when we go down this graph, we're losing energy, right? And so here you can see that the phase is changing, but there is no temperature change, right? So the temperature will not change, but the phase will, and that's true down here as well. This one, the phase does not change, but the temperature does change, all right? So that's good. Let's do a few problems that like you might see here. And before we do that, though, I should tell you that these numbers, what they are. So the molar heat of fusion is this number here, 6.01 kilojoules of energy per mole. Okay, so that means that if you have 18 grams of ice, you would have to apply 6.01 kilojoules of energy to that 18 grams of ice to get it to turn into liquid water. And then this is known as the molar heat of vaporization right here, 40.7. It's a big number, right? And it requires a lot of energy to go between liquid and vapor. And so if you had 18 grams, that's 1 mole of liquid water, you'd have to put a ton of energy, 40.07 kilojoules of it, to get that to turn into steam. Okay, which also means that as steam condenses back into water, a ton of energy is given off. That's why steam burns are so bad. So anyway, be careful of steam, because once it turns back into water, it's releasing a lot of energy. Okay, so let's do some problems here. So these are like what you're going to see on your practice work. So here's the first one. Calculate the energy in kilojoules required to completely melt 30 grams of 0-degree ice. Okay, so 30-degree ice. 30 grams of 0-degree ice. That means that it's right at its freezing and melting point. So how much energy do we have to put in? And here's the schematic that you use. It's just a little 3-part dimensional analysis graph here. We put our grams of water right here. This little stretch of the graph is converting between grams and moles. We would divide by the molar mass, right? And then this is our molar heat of fusion value, which we're going to multiply by the number of moles of ice there are. And so in this problem, it ends up looking like this. We have our 30 grams of water. Okay, 30. We're going to multiply it by the 6.01 and divide that by 18. And that gives us 10.0 0, I'm just going to say 10 kilojoules of energy. Okay, so it takes 10 kilojoules of energy to completely melt that ice into water. But keep in mind, and I'm going to go back to this graph here, that is, we're basically looking at this stretch. We've got our liquid here and our solid here. Okay, so you'll see that we haven't changed the temperature at all. We've just moved along this scale from solid water to liquid water. So the phase has changed, but the temperature has not changed. It's all at 0 degrees. Okay, here's another question that's similar to that last one, although this will be a heat of vaporization type problem. So we're going to calculate the energy released as 75 grams of 100-degree steam, so that's the gas phase of water, condenses into 100-degree liquid water. So again, we're not changing the temperature, we're just changing the phase. And so that means that we are working up here at this end of the graph, and it's got a different value. That heat of vaporization value is different than heat of fusion. So here's what the setup looks like. You're going to put your grams of water given to you in the problem right here. Same setup here. This is just, again, converting between grams and moles of something. And then we're going to multiply the number of moles by the molar heat of vaporization, which is 40.7. And here's how those numbers stack in. We've got our 75 grams of water multiplied by 40.7. And then we're going to divide that answer by 18. And that is 169.6 kilojoules. Okay, so these vaporization problems are much, much bigger answers than heat of fusion, just because the heat of vaporization is just so much greater. Okay, and then there's a really tougher type of problem that you'll do as well, and that is where you take the whole graph into account. So here's the last question we'll do. This one says how many kilojoules of energy are released as 150 grams of 100-degree vapor completely freeze into 150 grams of 0-degree ice. So if you think about our graph again here, here's what we know to look at. We're basically starting all the way over here. This is all vapor, this is all liquid. And so we're taking 150 grams of 100-degree vapor, and we're first phase changing it into a liquid. And then that 100-degree liquid we have to completely cool off into a 0-degree liquid, and then we've got to freeze that into 0-degree solid. And so for each stretch of the graph, we have to do its own problem. So up here, the first thing we would do is start with our 150 grams of water. This is 18 grams per mole, because we're working with water. And then the heat of vaporization up here is 40.7 kilojoules. Okay? Down here, since this is what we've been working on so far, this is the 150 grams of water again. This is 18 grams per 1 mole. And this is 6.01 kilojoules. Right? Okay, so we've skipped this whole big stretch of graph though, but that's the kind of work that we already know how to do. This is delta H equals 4.2 times 150 times 100. And so this is the amount of energy that's going to be given off as this water cools off. And then these other flat parts of the graph, remember the temperature does not change there. The problem here is that the answer you're going to get here is in joules, and the answer you get with these guys is in kilojoules. Right, so that's why I'm asking how many kilojoules of energy, because we're going to calculate this and then convert this one answer into kilojoules, and then we can just add them all up together. Okay, so let's just solve these. This is 150 times 40.7 divided by 18. This is 339 kilojoules. Okay, so that answer, we're going to do 4.2 times 150 times 100. And by the way, I might have glanced over it. The 100 that you see right here, that is the temperature range from the boiling temperature down here to the freezing temperature. So there's 100 degrees. This is your delta T, right? And that gives us 63,000 joules, which I'm just going to divide by 1,000 to make it kilojoules, and that is just 63.000. That gives us the similar unit to add up. And then down here, divided by 18, this is 50.2 kilojoules. Okay, so now these answers that are circled represent all of the energy values as the water changes. First, its state from vapor to liquid. Then it goes from 100-degree liquid to 100-degree solid. 100-degree liquid to 0-degree solid. And then from 0-degree solid to, 100-degree liquid to 0-degree liquid. 0-degree liquid to 0-degree solid. Okay, sorry. So let's add up these numbers. We got 50.2 plus 63 plus 339. That gives us a total answer of 452.2 kilojoules. Okay, and of course, if we're going from hot to cold, like we are in this problem, this is an exothermic value, right? From lots of energy to little energy, that's exothermic. So anyway, that's how you do those problems, and hope this helps.